Hello everyone, class 12th, the topic is SN2 mechanism. In previous video we have understood SN1 mechanism of nucleophilic substitution reactions in haloalkane. Now here we have SN2 mechanism. Let's understand the meaning of SN2. S represents substitution, N represents nucleophilic, and 2 is representing bimolecular, means two molecules. What does it mean? Let's check. We know nucleophilic substitution reactions are this: Rx plus Nu, incoming nucleophile, stronger nucleophile than X, it will replace it and X will release out. Now this is reagent number 1, this is reagent number 2. Now both reagents are deciding speed of the reaction. Speed of reaction directly depends on concentration of Rx and concentration of nucleophile. Two reagents are deciding speed of the reaction, that's why it is bimolecular. Like in SN1, only one molecule was deciding the speed of the reaction, so we call it unimolecular. Let's check further. How SN2 mechanism happens? It is single step mechanism. SN1 was two-step mechanism, whereas SN2 is single-step mechanism. In this mechanism, what is happening? We know Rx, haloalkane, X is more electronegative, negative charge, positive charge. Incoming nucleophile with a lone pair is attacking from the back side. This carbon is a target of nucleophile, so nucleophile is attacking from back side. What is the meaning of back side? Opposite of X, the direction which is opposite to X. Why it is not attacking from front side? Because this side, who is present? A negative particle. Nucleophile itself have a lone pair and carrying sometimes negative particles are also there. Nucleophiles are of two types, negative and neutral. So when it will attack from this direction, in front of it, who will come? X. Negative, negative. Repulsion will happen. That's why nucleophile is preferring to attack from backside. Now after this backside attack, this attack is not possible, so I am cutting it. After backside attack, a transition state will generate. In this stage, what is happening? Incoming nucleophile is making bond with R and outgoing X is breaking bond from R. Means bond making and bond breaking is happening simultaneously. This is we call transition state. Now, hybridization. Here the carbon hybridization will be sp3, but in transition state carbon hybridization will be sp2. We know what is sp2 hybridization. Around carbon 3 orbitals will generate, which we call sp2 orbitals. With these orbitals it will make bond with hydrogen. Hydrogens will be there. When I will use actual molecule, you can easily understand hydrogens will be there around carbon. Those hydrogens I am writing here. Between these lobe, angle will be 120 degree and the geometry will be triangular. In 11th class, we have done all these things. Now, because carbon have total 4 orbitals in outermost shell, 2s2, 2s and 2p3. Out of those 4 orbital, it is using 3 of them, sp2 as sp2, sp2 and sp2. One p orbital will remain unhybridized. In these p orbitals, nucleophile incoming and outgoing X are involved. Actually, the carbon was like this: sp3 hybridized, sp3, 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 hydrogen, hydrogen, hydrogen and X. When nucleophile attack from backside, its hybridization change. This sp3 hybridized orbital will become normal p orbital, and sp3 orbitals will become sp2. So geometry will also change. It was tetrahedral. Now it will become triangular with a perpendicular p orbital. And we know p orbital have two lobes, in which one is with X and other lobe will be attacked by nucleophile from backside. So this is the condition of carbon over here. Charges, if I will talk about charges, the nucleophile was complete negative charge. When it start making bond with R, so its negative charge will become partial negative. X is not completely left carbon, so that's why still it is carrying negative charge. So this is a transition state we have in which hybridization of carbon is changed from sp3 to sp2. Now after this, finally what will happen? We know X completely leave R and nucleophile will make complete bond with R. Final product will be generated. In this fashion, the SN2 mechanism is happening over there. Let's check the factors on which SN2 depends. Factors. The first factor is nature of Rx. This is methyl halide, smallest haloalkane. This is 1 degree halide. Now let's try to understand between 1 degree and methyl, which is more reactive toward SN2 mechanism. We know in SN2 mechanism, nucleophile is attacking from backside. Let's draw this these hydrogens like this. The target of nucleophile is this carbon because it is carrying a positive charge. It wants to attack on this carbon. Similarly here, nucleophile wants to attack on this carbon. Now please check. This carbon is surrounded by 3 hydrogen atoms. Hydrogen atoms are very, very small. So they are not creating too much steric hindrance, or simply we can call it crowding. So here nucleophile attack is easy. This nucleophile can easily attack on this carbon because steric hindrance means crowding around carbon is very, very less. But where we have 1 degree, so you can check 2 hydrogens are there, small atoms are there, but also we have a bigger CH3 group, bulkier CH3 group. So here steric hindrance around this carbon is more. Don't you think if we will proceed to 2 degree case, this is 2 degree haloalkane, positively charged, nucleophile wants to attack, but nucleophile will face problem of steric hindrance. 2 bulkier groups are over there and 1 small hydrogen atom is there. So this nucleophile will feel difficult to attack on this carbon. And as we will go for 3 degree, this problem will be further increased. So if I talk about reactivity order, of nucleophile by SN2 mechanism, so 3 degree haloalkanes will be least reactive, 2 degree haloalkanes will be more reactive than 3 degree, 1 degree haloalkanes will be more reactive than 2 degree and 3 degree in SN2 mechanism, and methyl halides will be most reactive toward SN2 mechanism because nucleophile is attacking from backside, and if we have crowding on a backside, then there will be a difficulty for nucleophile to attack on carbon. That difficulty is maximum in 3 degree case and least in methyl halides. That's why methyl halides are most reactive toward SN2 mechanism. Next factor, nature of nucleophile, incoming nucleophile. This easily we can understand. Strong nucleophiles can easily attack from backside as compared to weak nucleophile. What are strong nucleophile and what are weak nucleophiles we have already discussed in previous videos. Strong nucleophiles are those which can donate their lone pair very easily, and weak nucleophiles are those which can't. So obviously strong nucleophile can attack on carbon of Rx very easily but not weak. So nature of nucleophile also decide SN2 mechanism. Third factor, polarity of solvent. SN1 mechanism was favored by protic polar solvent, and SN2 mechanism will be favored by aprotic polar solvents. Reason, if we are using protic polar solvent, nucleophiles are charged particle, negative charge they have. Also polar non-charged particles we also have as a nucleophile. X as a negative, R as a positive. Now if we are using protic polar solvent, what are protic polar solvent? Like H2O, in which polarity is there as well as proton is available, means H positive ions are available. So what these H positive ions will do, they will start making hydrogen bonding with given nucleophile through their positive charge, due to which its movement will become slower. We call it solvation of nucleophile. If nucleophile is surrounded by or holded by water molecules, how it will attack on Rx? Its freedom will be decreased. That's why we don't prefer protic polar solvent. We prefer aprotic polar solvents in which H positive particles are not available, like CH3CN, ethane 1 nitrile we can use as a solvent, CH3 2SO dimethyl sulfoxide we can use, in which we don't have H positive ions as which can hold the incoming nucleophile. So we will have to use aprotic solvents for SN2 mechanism. And the last factor which affects SN2 mechanism is nature of leaving group. Leaving group means X. We know Rx is of 4 types: RF, RCl, RBr and RI. Which nucleophile can leave the molecule easily? In SN1 it was also discussed, I negative can release or leave the R very easily. That's why haloalkanes are more reactive than RBr in SN2 mechanism, and it was also more reactive in SN1 also. So nature of leaving group is common in both mechanisms, SN1 as well as SN2. It is common with same reason. So that's it. This is the end of SN2 mechanism and the factors which are deciding SN2 mechanism. Thank you very much.